Hello everyone. This video covers problem of the week number 3 for the summer session. For the first problem, we're going to use integration by parts. Now here is very tempting to pick u equals to x cubed and then say that the u is 3x squared, and then try to do just substitution. Like this will be du over 3. This is completely wrong, so you shouldn't do anything like that. So instead, you need to break this into two parts so you can do the integration by parts. Now there are multiple ways to do this, but probably the easiest way is the following. You should rewrite. So you're going to rewrite the integrand x cubed e to the x squared as x squared, and then you're gonna borrow x from here, so it will be x e to the x squared, and then this will be u, and this will be db. So if we pick u to be x squared, then du will be 2x, and if dv is x e to the x squared, that means b will be 1/2 e to the x squared by using substitution on this one. Here u will be x squared, so the u is 2x the x. So if you integrate this, you'll end up with something like this. Notice that the 2's will cancel, so pretty much what you have is this 1/2 x squared e to the x squared minus the integral of x e to the x squared dx. But notice that this is pretty much exactly this integral right here. So therefore the answer should be the same. So from here we'll get the integral. It's going to be 1/2 x squared e to the x squared minus 1/2 e to the x squared, then plus c. You can factor this if you want to, but it's not necessary. So this is the final answer. Again, you can factor e to the x squared if you want to, but it's not necessary. It looks nicer, it looks cooler, but it doesn't have to be factored out. All right, let's go to part B. And this problem, you will find out too that you can only do this problem also by using integration by parts. So first thing, just call all of these equals to I, and notice that I has the minus sign, just don't forget that. Again, we're going to rewrite minus cosecant qx as minus cosecant x squared times cosecant x. It doesn't matter which one goes first, you just have to keep track, so that will be times cosecant x. And then we're going to use integration by parts. So let's say that u is cosecant x, so du, remember, it's minus cosecant x cotangent x. And then if we choose db to be the remaining, which will be minus cosecant square x, the x, well, then b is equals to just cotangent x. Why? Because the derivative of cotangent is minus cosecant square. All right, next we use the integration by parts. So integration by parts, just like we did in the previous one too. So remember, integration by part is ub. So in this case, it will be cosecant x, cotangent x, minus b du, where du is minus cosecant x, cotangent x, dx. If we simplify this, we end up with cosecant x, cotangent x, then the minus here and the minus here, it will give you a positive. So this is plus the integral of cosecant x times cotangent square x dx, because you have cotangent plus cotangent, it will give you cotangent square. Next, we're gonna need an identity. Okay, so recall the 1 plus cotangent square x is equals to cosecant square x, which means the cotangent square is cosecant square x minus 1. Therefore, if we use the identity here, we'll have cosecant x, cotangent x. That part is not going to change for the rest of the problem. Plus, now this will be the integral of cosecant qx dx minus the integral of cosecant x dx by distributing in here. So if you multiply this by cosecant, you'll get cosecant q and then cosecant square, just cosecant dx. Next, you have to be very careful with this part. Remember that we call I equals to minus this integral, which means that this integral is equals to minus I. So that's very, very important. Otherwise, things will cancel out. So that means this is technically minus I, which is what we're trying to find. And then also recall that the integral of cosecant x dx, and this is given on the formula sheet, this is equals to ln of cosecant x minus cotangent x. Therefore, if you move the minus I to this side, remember the integral we're trying to find, we call it I. So if we move this to this I, so it's going to change the sign. So I plus I, it will give you 2I. So we'll end up with 2I. Remember that what you want is I only, okay? And then this will be equals to cosecant x cotangent x minus the integral of cosecant x, which is equals to all of this. So this will be minus ln cosecant x minus cotangent x. So therefore the final answer will be I is equals to 1/2 cosecant x cotangent x minus 1/2 ln cosecant x minus cotangent x, and then plus c. Don't forget that part. And that's it. All right, let's move to the last problem. All right, this is very similar to the very first problem we did. So Mickey Ratz claims that this cannot be integrated. Is he correct? And the answer is yes. We could try first like eliminate substitution, but substitution doesn't work. And it doesn't work because of this. You have technically two substitutions. You could say u is equals to x squared. Then du is 2x dx. So this is not going to work. Or you can say, okay, well, let's let u equals to x squared. then du will be e to the x squared times 2x dx, which also doesn't work. So therefore, our last resort is to use the same trick from number 1, part A. And that was this. Remember, you can say, well, let's rewrite this as x times x e to the x squared. Because we already know integration by parts will work for this part, or so it looks like. So let's see what happens. So let's say we call u x. So du is the x. So far everything looks good. And then let's say that db is equals to x e to the x squared, and we already saw that this is equals to 1/2 e to the x squared. So far everything looks. Then there is an issue, and the issue is right here. So from here, if we use integration by parts, this will be ub minus b du. So therefore this is 1/2 x e to the x squared minus 1/2 the integral of e to the x squared dx. However, this is a very special integral, because you cannot find a function that when you take the derivative will give you this. So this pretty much doesn't exist. So there is no fundamental function that will give you this. So that's why this is impossible to integrate using the traditional methods. You can approximate this numerically, but that's a different story. You will see that in section 8.9. But the way this is given, without limits of integration, you cannot integrate this. So this is impossible. So therefore, that implies that Mr. Ratz is correct this time. By the way, as a side note, if you do higher math later or statistics, if you change this to minus x squared, it's pretty much the same story, but if you put limits of integration from minus infinity to infinity, then you can integrate this. So then this is possible. Some of you in the solutions put the error function, which is technically correct, but you can actually find this, and this is technically the basic integral for probability. But again, this is just a side note, so you don't have to worry about this part. And in calculus 3, you can actually integrate this using polar coordinates.